Okay, we now have a talk by Dr. Justin Pierel, who is a postdoctoral researcher at the Space Telescope Science Institute. The talk he'll be giving today is SALT-3 near-infrared, taking the Type Ia Supernova Cosmology workhorse to longer wavelengths. And I see your screen already up there. Thank you very much. And whenever you're ready, thank you.
Great, thanks, Rebecca. And yep, today I'm basically going to talk about Type Ia supernova cosmology in the near-infrared in the context of Roman, of course. And it's had a few great backgrounds now, basically, from, in particular, Dave Jones, and then in the previous talk as well. So I'll just start with a general question of why are we interested in Type Ia supernova cosmology in the near-infrared, which Dave touched on as well. Because most of the major cosmology studies of the last 20 years or so for Type Ia supernovae have happened in the optical. And there have been a few studies over the last 5 years or so in particular, but also in the last 10 or 15 years, showing that there's value for using rest frame near-infrared observations of Type Ia supernovae for cosmology. So here I'm showing two independent studies of that, where any rest frame near-infrared observations basically reduce the statistical uncertainty on any individual distance measurement. So red in both cases have some near-infrared data, and blue and green in both cases are optical. And so, you know, it's maybe not that surprising that for some of this reduction in uncertainty comes from the lower sensitivity to dust, at least, which leads to these more precise distances. In addition to that, though, as was mentioned in an earlier talk, that we need to do these, and in the previous talk, we need to do these stretch, in particular, measurements of 1A light curves in order to make corrections to apparent brightnesses to make accurate distance measures. And it turns out that in the near-infrared, there is not a huge relationship between near-infrared data and the optical stretch parameter here on the x-axis, which means that even without making a stretch correction, you can get an accurate distance measure, which means that Type Ia supernovae appear to be relatively true standard candles in the near-infrared, as opposed to these sort of standardizable candles in the optical that require these shape and color corrections. So with this kind of context in mind, I'm going to answer three questions. So first, of course, SALT was in the title here, so I'll just briefly describe what SALT is and why we should keep using it, at least in conjunction with other models, why we need a new version of SALT and how we're going to get there, and what a fully trained near-infrared SALT model gets us. So I'll obviously start at the beginning here, and that's just describing SALT, which just stands for Spectral Adaptive Light Curve Template. It's just a relatively simple empirical model of Type Ia supernova light curve evolution. It describes the flux of the supernova with time and wavelength in this sort of principal component way. So it has this m0 component, which is in red. It basically just describes sort of a normal Type Ia supernova evolution. And then there's a M1 in green, which is sort of deviations from that baseline M0 component, and a color law as just a function of wavelength in blue. And these components come from this same stretch color correction. So M1 handles the stretch of a light curve, and the color law handles the color. And so this, you can see in the background, is SALT-2. It's been around since 2007. And it's been used in a series of cosmology studies in the last 15 years. We are now on SALT-3. So this was work done by Kenworthy et al. Last year. You can see the original training sample here on the left for SALT-2, extending to about 8,500 angstrom. The new data added this in to get us to about 1.1 micron. So here's the full sample here on the right. And the addition of all the data here basically gave us a lower color scatter across all wavelengths, as well as this extension into the near-infrared. And as David mentioned this morning, the addition of just that Z-band gives us like a 20% increase in the amount of Roman data that we can actually use. So we've already heard about kind of alternative ways to measure distances from SALT, and I think we'll probably hear about some more. So why do we want to keep using it? Why not just move on from SALT to something that maybe provides more accurate distances, or has better coverage or whatever? So here's some reasons that we want to continue the framework. So one, it's made up of a heterogeneous spectral and photometric data set. So it leaves it a little less susceptible to potential biases in the training sample. It has a pretty extensive phase and wavelength coverage compared to some alternative optical models. That is obviously something that we want to continue extending. It's very well vetted. We have a good handle on SALT's limitations and advantages because it's been used in basically every major cosmology analysis in the last 15 years or so. Provides native K corrections. It's integrated into major simulation frameworks like SNN that's already Phil described a couple talks ago. It has an open source training sample and code, which means it's easy to test potential biases in the training sample, as well as continue updating the training over time by adding new data. And there are more reasons, but I think it's sufficient to show that while it's definitely a good idea to have more models in the optical and near infrared and continue improving the ways in which we measure distances, there's still value in having the SALT framework around and continue improving it into the future. So that's SALT and why we should keep using it. So on to why we need a new version. Why can't we just stop at SALT 3 and call it a day? And how are we going to get there? Well, of course, a Roman conference. So here's the Roman filter set with the SALT 3 coverage superimposed. So you can see that even with this extended wavelength range to 1.11 micron, we are throwing out about half the data here. As a result of knowing that we'll be using SALT at least in part, as well as other optical models for cosmology, the current Roman high latitude time domain survey that Phil described produces some distribution of 1As that looks something like this that you've already seen. And you can see that there's relatively few supernovae at low redshift taking advantage of this terrestrial near infrared because we aren't really geared up to use it. Even with some near infrared light curve fitters, we don't have really like the near infrared cosmology pipeline set up and understanding how to exactly do this as well as with the optical. And you can see that rest frame near infrared data from Roman will exist all the way out to redshift 1, where SALT 3 and other optical models will not be able to utilize it at the moment. So that's why we need a new model, is this trend towards using the near infrared, and we're getting more and more near infrared data coming up. So how are we going to get there with a near infrared SALT model? Well, it's a full spectral model. So in addition to the photometry that exists in public repositories, since this is a public training set, we needed a series of near infrared spectra with sufficient quality. And that has not really been possible until now. So that brings us to HST. So here's the WFC3IR wideband filters and Prism superimposed on this SALT 3 wavelength range here. So you can see ends about 1.1 micron. And so data from this, from WFC3IR gets us basically all this complementary range of both spectra and photometry out to about 1.8 micron. And that's what we've done. So two major HST programs, Raisin, which David described earlier from cycles 20 and 23, gave photometry on a few dozen 1As out to redshift 0.7 or so in near infrared filters, and Syrah, a low redshift 1A program that provided GRISM, spectra, and near infrared photometry in all of those filters for a couple dozen supernovae. And that together has given us, in conjunction with the public ground-based data, has given us enough coverage here. So here's the updated training sample on the left with coverage across the same phase range, but now out to about 2 microns. So this gap being just because this is central filter wavelengths. And so here on the right, the old SALT 3 coverage and the new SALT 3 near infrared coverage reaching about 2 micron. So that's how we're, why we need a new version of SALT and how we're getting there is with these HST programs. So what does that actually get us, having this near-infrared SALT model? Well, the bottom half of this plot David actually showed, so you get another view. The same idea of reducing statistical uncertainties by adding near-infrared filters, which effectively gives us an increase in the sample size at low redshift, even without re-optimizing the survey for rest frame near-infrared observations, just by reducing the statistical uncertainties on each distance measurement. And then this top half is new, which is showing just that the low redshift and then moving to redshift of 1, the usage of the Roman filters by SALT3 versus what SALT3 near-infrared provides, where at this low redshift range in particular, you can only access 2 of the bluest filters with SALT3, whereas you immediately have access to 5, and then all 8 by redshift of 0.3. This combination is basically where I'm going to stop. And so I'll just finish by saying that I think the near-infrared is an exciting frontier for 1A cosmology, and I love to see all of the different ways in which people are working to make sure we can fully harness the rest frame near-infrared with Roman. This training of SALT in particular in the near-infrared is really only possible for the first time now with the advent of these new HST programs. And we'll now be using SALT3 near-infrared to help optimize the survey further, as well as now leveraging the full Roman wavelength coverage at low redshift with the SALT framework. Thank you.
Thank you very much for your talk, Justin. That was wonderful. Do we have any questions? So I'm just checking in the Slack now. I don't see any on the thread. Oh, we have some. Pat Morris is currently typing one, so I'll wait a moment for that question.
Okay. Type faster.
No pressure. Okay. This is actually for Eric. So that is not for this talk. So Eric, you can address that online. Do you have any questions for Justin currently? Nope. Okay. Well, I'd like to ask a question if that's okay. Okay. So the Type Ia supernovae in the near-infrared, they're supposed to be more standardizable candles. Is that correct, potentially? There's been talk about that more?
Yeah, I think the main thing is that even without corrections, they're already fairly standard candles. So Dawan et al. In 2018 found that just using, just fitting basically peaks of the light curve and applying no corrections was still able to get a relatively precise measurement of H0 relative to a much larger optical sample. And so what SALT3 near-infrared can do is go the next step and say, they're already good standard candles alone, but we can still apply the SALT framework of even a relatively small shape and color correction by combining with the optical and get even more accurate measurements. Yeah.
Awesome, wonderful. Well, I look forward to seeing the result of your work, and thank you very much again.